That now we have Lec servers full of computing servers, and we can make a Lec server full of storage server. And now the next challenge is how do we connect those servers based on networking infrastructure so that a compute server is able to store data on the storage servers. Not only that, so that your compute server delivers good network performance to the users who are using those servers from the internet, the way which is the main philosophy for cloud computing. So we need some nice methodology to network your data center hardware devices. Okay. And as you see in this picture, on the data center blade server, you run a lot of different kind of application and services, including a web server, a mail server, a gaming server, a chat server. Companies like Google, they run indexing and search server, and based on what kind of services and application they're running on your blade servers, you have different network requirements. Not all applications are the same. For example, if you have a compute-intensive workload or services running in the blade servers, which is like high-performance computing, that you normally see for scientific computation like high-energy physics, or in case of biological modeling. So those kind of application needs a lot of compute power, but they don't need so much inter-server communication. So in this case, if the data center is going to be used for those kind of workload, then what you need to do is you need very powerful compute blade server, but you can have medium range networking device because those applications are not going to use too much network. However, if you are data intensive service hosting like YouTube, for example, on your data center, if you're running YouTube services, YouTube application, there's video on demand. So as you see, these video files are very large in the size, and if you want to transfer these video frames from data center in London to all the way to here, you need, of course, a good internet connectivity between the user and the data center, but you also need good connectivity inside data center. So in that case, you need to have some high-end switches that connect to your compute server where you have hosted your streaming server to the storage server where you actually have the video files, so that you can take the video files from the storage server and stream to the user. So you need good network connectivity for data intensive. And in some sense, most of the data center are balanced because the whole idea of data center is you run multiple kinds of workload together in different virtual machines. So you will have compute intensive, network intensive, data intensive, everything working together. So you have to come up with a networking approach that balances different demands of application at the same time while delivering good network performance. That's a hard challenge. How do we do that? And what kind of topology we need in order to scale your networking to this multiple kind of workload, at the same time scale networking to thousands of physical server and hundred thousands of virtual machines. So it's a very complicated job how to design data center network, and there are a lot of requirements that you have to keep in mind if you're a cloud network engineer. So just as a background, if you have done the core distributed systems or computer network module, these are the types of topology that you use, that you study. For example, this one is called the ring topology, where each computer is connected to its intermediate neighbors. So if this computer wants to send message this one, it goes through all the neighbors. Similarly, with the bus topology, it just forwards to the next neighbor. The problem with this topology is they're not scalable. So they can handle a network communication in a local area network such as your computing lab where you do the coursework, but if I want to use these topologies to connect thousands of servers, they are not scalable. So that's the reason the data center engineers, they come with a new topology that we studied together that meets certain requirements, and that topology is called factory topology, which has its own principles based on how many switches you need at different layers for data center, how they communicate, what should the bandwidth, because these existing topology that is present in a local area network cannot scale to massive scale data center, so they cannot use it. For example, If someone uses star topology, I just see that everyone is connected to one switch. If it does just to one switch, if I connect 1,000 servers, the switch will be overloaded and then the load servers can reach each other, and the data center is not scalable. So we cannot really use these topologies to connect our data center servers and the storage. So in the cloud data center, if you want to design the network, you have to keep certain design goals in mind. And whatever network you design has to support these properties. So these properties are not same for what a cloud computing has to support. So this properties is for a network that needs to have this property in order to support the cloud computing features. So that we will study after after 10 slides, what are the features of cloud computing. But in order to support those features of cloud computing, your network has to support these features. The first one is availability and fault tolerance. So for example, one of the students asked me in the break, what happens if a network link between the compute blade server and the storage blade server fails, how it's going to work. So what they do is they replicate the link. They don't only have one link, they have multiple links. For example, they can always have a failover if one of the links fail. Not only that, in addition to replicating the network link, they also replicate the servers itself. For example, if I have this whole rack failing because of the network switch, then the same content and the same computing capacity is offered on the other server rack where you can redo the computation. So how do you think they can do it? How can you replicate the computation in a cloud data center? So if I am computing something here, and suddenly it fails, and I want to say migrate that to the next blade server, how can we do that? Can we just migrate a physical server? We cannot, right? Someone can't run in, take this blade server and put on the next rack. You cannot do that. So they do it through virtualization. So when you study the Docker, the container virtualization, what you can actually do is, if your container is running on one blade server, you can suspend it, take the snapshot of it, clone the container, and then copy that as a file to the next rack and restart it. So they use the power of virtualization to create higher availability and fault tolerance. This is at the level of computation, but at the same time, you need that at the level of networking, and that can only then to have some redundant links, more than one link to support different blade servers. So that's one of the design requirements you have to keep in mind when you design the network infrastructure. The second design goal is scalability. So as I said, in a local area network, we have maybe 10 or 20 or 30 servers. In data center, we have thousands of servers. So whatever networking design that you come up with has to support this ever-growing scale of networking requirements. And you may start today with a data center of 1,000 servers, but tomorrow it can become 2,000 servers or 3,000 servers. So you have to come up with a design that can scale on demand. So your scalability is another feature that you have to keep in mind when you design data center. In doing so, other important cost is the low cost. Because ultimately, a cloud provider, by putting the blade servers and storage servers and networking, they release it to third party, and they, as with any business, they want to make profit. So they don't want to spend too much money on networking or servers. So low cost is one of the other important criteria that we keep in mind. So this is one of the key in cloud computing, the cost to performance ratio. How much cost you want to put on your data center infrastructure that doesn't compromise the performance of the user so that you get enough users. So how to compute the cost to performance ratio? Again, this is done through benchmarking that we'll learn in third or fourth lecture. So you have to come up with a cost model and the performance model for each of your data center resources, your compute server, your storage server, your networking server, and based on that you decide how much expensive network switches I need, how much expensive blade server I need, how much expensive storage server I need, so that I give sufficient performance to my user. At the same time, as a cloud provider such as Amazon and Google, I still make a profit. Because ultimately the goal with any business is to make profit, so that you have to keep in mind. You have to make sure that your data center network delivers good throughput, that is number of data packets or request transfer per unit of time. So again, how to determine the throughput? Through network benchmarking. So you have to create different kind of network workload, compute intensive, data intensive, balanced one, and then load that traffic on a data center network, and then say under the saturation point, what is the saturation point for my network when all the workload are at their peak? So you have to do benchmarking to figure out your average throughput, max throughput, and minimum throughput based on different scenarios of workload, and based on the decide what kind of switch capability you need. And obviously you have to come up with such a topology that can decide, that can take benefit of economies of scale. The economies of scale means you have a huge data center with thousands of servers, but you want to make sure that your network has reached to as many servers as possible, but while minimizing the cost. So you have to come up with some model to exploit the economies of scale while designing the data center network. You also have to take care about the full bisection bandwidth of your data center network. So what is a full bisection bandwidth? I will define it when we learn about the factory topology that they use to create the data center network. In that factory topology, how to determine the bisection bandwidth, we'll go into that. But this is one of the design criteria from host to host. From rack to rack communication, you have to take care of the bisection bandwidth. And the bisection bandwidth should not lead to oversubscription or undersubscription to be able to make profit. And the last goal is the load balancing. So how many switches you have, as many network paths that you create in the data center, you have to make sure that all network paths are used at optimal level so that you don't waste any resources, and all network path has equal traffic so that you avoid the hotspots and the failures. So load balancing, network load balancing is the other thing that you have to keep in mind when designing network data centers, networks. So most of the data center, they either use 2-layer topology or 3-layer topology based on how many hosts, storage hosts and the compute hosts you want to support in the network. If you use the 2-layer topology, you can support up to 8,000 server blades in your data center. If you use 3-layer topology to connect your network, you can use you can have more than 25,000 hosts in networks. How do we do this 2-3-layer? I will discuss next. And mostly, when you create multi-level topology, at the higher level, you use more powerful switches with auto ports. So you use 10 gigabit switches with almost 128 ports. On the lower level, you use 1 gigabit switches with 48 to 288 ports. Why do you think at the higher level we use more powerful switches than the lower level in a multi-layer topology? What could be the reason for that? That's why it's called a factory, right? So on the up you have much more powerful switches because it has a connection to all the lower end switches. So that's why on the upper end you need more aggregated bandwidth as compared to the individual blade service. So individual blade rack units could be connected on the small switches, but all of them connect to the upper level switches. That's why they need more powerful bandwidth to be able to handle the traffic from coming from lower levels. And all these 2-layer and 3-layer topologies, they use a routing mechanism called equal cost multi-path routing called ECMP. So this is not TCP/IP. Okay, TCP/IP is the underlying protocol that is used for sending messages from one host to another host. But ECMP is a policy that is used to route the traffic from one switch to another switch in a data center. So it's not same as TCP/IP. So what pretty much ECMP does, it balances the traffic flow across multiple network paths. And the main principle behind ECMP is it will choose, so if you have two network paths that has same bandwidth and same number of hops to reach a destination, it can randomly choose one of them. So this is what I call equal cost multi-path. So if two network links have same configuration, the goal of this routing methodology is to select one of them on the random. And by doing that, the experiments show that it can create near to optimal network load balancing in data center network. So most of the data center administrator will implement DCMP routing to balance traffic across different servers. Of course, there are problems with ECMP as well. The routing table can grow very large based on how many switches you have and how many servers they connect to. So there are different optimization to counter that we will discuss now, how they deal with growing number of routing table or growing latencies. But most of the data center provide they implement ECMP to balance the traffic across different switches in different parts of the network. Right, so I was talking about this multi-layer and two-layer architecture. So which one is this? Is 2-layer or 3-layer? Come on, this is very obvious. It's 2-layer or 3-layer. It's even written there, 3-layer. Maybe it's 6 o'clock, that's why. Right. But I have to teach because we go till 6:30, right? Okay. So this is the 3-layer topology. This is divided into core, aggregation, and the access layer. Okay. My next question is, in this diagram, where is our blade servers? At which layer? But that's again obvious. Where are our blade servers? Where are our storage servers? Of course, at the access layer, right? Right here. And why this is called as a fat tree topology? Because the switches at the top on the core layer are fatter in the sense that they have more bandwidth to connect, more number of ports to connect to lower level switches. So what do you see as the distinctive feature of the core switches here? Answering a question. So what is the distinctive feature of the switches? Each switch is connected to each of the aggregation switches, right? So in that upper layer switch, even 3 of the top switch fails, still you can reach your network. So this is one of the main feature of fat tree is that you have so many ports and so much bandwidth available that if any of those 3 fails, still you have reachability to your servers because they are redundant, right? But what if some switch on the aggregation layer fails? Can you still reach your servers? So if these 2 switch fails, can we reach here or no? So what could be a way for that? Normally they don't implement redundancy at this layer because you already have 2, right? Each of them are connected to it. So even one of them fails, you can still reach here. So they have one level of redundancy, but if both of them fail, then this part of data center is gone, unless you fix it. So one way is to you can short circuit these 2 other switches, but then again, it's not scalable. So that's the trade-off. We have scalable versus the failover. So they have failover at the core to aggregation layer, but they don't have so much failover from aggregation to access network. So what is the failover factor at the core network? 3, right? So 3 switches can fail, you can still reach the network. But at the aggregation layer, the failover factor is just 2. So if these 2 fails, you can't reach. What is the failover factor for each blade server? 1. If this one fails, this is gone. So as you go down, your failover factor decreases. But again, that's done in an explicit way because you can come in maybe in 10 minutes. You can start. You can start. So here's your lead demonstrator. So you will present your what you need to do with the coursework, which is also very important. So you will guide through that, right? So as a data center engineer, you got to decide how much failover you need at the core layer, how much failover you need the aggregation layer, and how much failover you need the access layer. Based on that, you decide how much you connect. And there is a mathematical formula to decide how many switches can support how many servers that we will discuss next. But of course, if you want no failure, then you can short circuit each of the switches together, but that's again, it's not scalable. It will become a star topology and then it will not scale to thousands of servers. That's why you got to follow this one. So as I said, if say this switch fails and I have some computation data stored here, what is my way to recover that? Just snapshot it and keep a copy of that. So maybe the snapshot is not current, maybe it's 10 minutes old or 5 minutes old. So they have this cloud providers, they have this rollover fail-safe mechanism. They keep snapshotting their computation based on what you're running here. Based on that, they snapshot the data. They don't need to snapshot everything. For example, if I'm just running the video streaming service here, then I don't need to snapshot anything because I can just transfer the user request to the next server because my video frame's actually sitting on some other server. So it depends on what you're running or that. Based on that failure, you do different actions. Right. So as I said, this is how the data center topology looks like. This is again the 3-layer architecture. I said it's a factory because the switches at the top are more powerful. They are faster than the lower switches. For example, switch on the core and aggregation layer, they are 10 gigabits, while on the access layer, they are 1 gigabits. And why they are fatter at the top? Because they, as compared to the lower switches, they handle more traffic. So that switches have to be more powerful. They have to support more data. They have to give more throughput per unit of time as compared to lower switches. That's why it's called as a fat tree topology. Right. So I would like you to think in this 3-layer topology, what's the value of k? So when you architect a fat tree topology, you always follow these formulas. And based on this picture, you should be able to find what's the value of k here. Because this k is a k fat tree structure that determines how many switches you have and how many servers you're connected to the lower level switches. So this k is very important factor. So based on this picture, can you figure what's the value of k? So just take one of the example, like each pod consists of k by 2 servers and 2 layers of k by 2 k port switches. Just take that example and try to find the value of k. So for this picture, what's k? Just try to put the number in the k and say it will satisfy all the conditions. K is 4. But whatever topology you make, you always have to stick to those 4 conditions, and based on that decide how many switches you will have at the core, at the aggregation, at the edge, and how many servers you connect to. So if you just take the k as 4, we can go through that. So each pod consists of k by 2 square servers. So k is 4, so 4 by 2 is 2, 2 square is 4. So each pod has 4 servers. Okay? And it connects to 2 layers of k by 2, 4 by 2 k port servers. So each layer connects to this 2 switches. So if you apply that 4, put in those equations, you will end up with, like the other one, a k by 2 core switches is connected to k ports. So k is 4, so 4 by 2 is 2. Again, 4 core switches connects to 4 ports. So whenever you make a factory topology for data center, you have to follow these formulas, and based on that you will decide. Based on this k value, you can decide how many pods you are going to have. So in pretty much a pod is a rack cabinet in which all the servers are there on one rack. This is defined as the pod. So in the exam, this could be asked. You can be given a picture and you may be asked to find the value of k, or it could be the other way around. I just fill that k number, and based on that I might ask you to draw the topology based on. So you really got to understand the relationship between the value of k and this topology. Okay. A fat tree has identical bandwidth across any bisection of the network. So I'll show you what I mean by bisection. So bisection means if this is your topology, at any layer if you draw a straight line that cuts each link into the half, the bandwidth on upper half and lower half are the same. Okay. So a bisection bandwidth is defined at sum of the bandwidths of the minimal number of links that are cut when splitting a system into two parts. So the bisection bandwidth of this part are same, this part are same, this part are same. So this is a nice about fat tree approach is that it gives you same bandwidth across different parts of the system, and that way you avoid the over or under subscription. So this is the reason why they use fat tree topology. This is not, you cannot achieve this in other topology like ring topology or bus topology or other topology. This is the main reason why they use fat tree. So why they use fat tree? One of them think you can achieve the same bisection bandwidth. Each layer, core, aggregation, and the edge layer have the same aggregated bandwidth. Each port supports the same speed as the end host, and all hosts on the leaf layer can see the same bandwidth across the system. And of course, based on the value of k, the topology can get more and more complicated. But of course, if you know those principles, you can always create your own k topology based on those. As long as you adhere to those equations, you will always end up with a balanced fat tree topology. Right, so this was fat tree within a data center, right? Now we talked about that these cloud providers have multiple data centers. So how do we connect those? Any idea on that? So Google has 15 data centers across the world. So they use fat tree to connect their server racks and storage racks within one data center. Now the next question is, how do we connect different data centers together? Can you use a fat tree on the scale of internet?
Point to point.
I mean, I'm asking, can you use a fat tree for the internet? So what might be the solution? They still need good network QoS. So what could be the approach they could be using?
Point to point.
Point to point. Maybe perhaps, yeah? You think these cloud providers are using the same internet as us to connect the data centers? So they have their own internet.
VPN, yeah.
Oh, VPN is just for securing the link. It's not. I'm saying that because they want to transfer hundreds of terabytes of data from one data center to another data center, like say YouTube, right? They are not going to use the internet because they will congest the whole internet, right? So what they can do to do that, they set up their own internet, backbone internet. So what they have done is following. So all this shows the map of internet, how different continents are connected through the optical fiber cable that goes in the sea. This is what we use. The poor people use these links, right? But as I said, because these cloud providers want to transfer a lot of data from different data centers, they can't use it because if they use the same links, it will congest the whole network and the quality will go down and nothing will get done. So what they have done is they have set up their own optical fibers in the sea. And these optical fibers connect the data center based on SDN, software-defined networking. So we'll have one hour lecture on that, why software-defined networking is a good way to manage your network. So software-defined networking used to virtualize the network. The way virtualization used to virtualize your servers, you have software-defined networking to virtualize the servers. So in this example, this blue line shows the Google optical fibers set by Google company, and they have invested more than £1 billion in setting up their own optical fiber network that connects different continents. And it's not only Google, as you see in this picture, you have optical fiber from Facebook, from Google, from Microsoft, and they all are building their own backbone of internet network so that they can efficiently transfer data and services between their data centers. So they're not using the internet to communicate between inter-data centers. They're using their own optical fibers to communicate between the new data center. As you see from this link, it's called Maria. It is owned by both Microsoft and Facebook. So each of them invested 500 million each to get that link through, and they both Facebook data center and Microsoft data center share that link to communicate with the data center. As you see, this cloud business is not buying few blade servers and start your computing. It's so expensive, right? If you want to enter this market, first of all, you need to have 1 billion to have your own network link before you can start your own rack server and anything else. So it's very complicated and a lot of money you have to put in before you can even think of becoming a cloud provider. Just before your data center starts communicating with each other. Right, so this is how the inter-networking between data center is done. Yes?
Why isn't any of that over the LAN?
Sorry?
Why aren't any of the cables laying over LAN?
So you mean, so I think what they have done is they have set up a data center near the sea where the first access point comes, so that they don't have to put over the lane. Because over the lane, there's internet to send data to you. Right. So for example, they will have one main access point in Southampton that connects to someone in South America, and then they will get all the data there. Because over the land is more difficult to put optical fiber because you have to dig and put. But in the sea, it's just you take a ship and just start throwing optical fiber. So over land would be beneficial for them, but it's just too expensive. Maybe it costs more and more billions. That's why they don't have over the land. So over the land, unfortunately, they have to use our poor internet. But they try not to use it. They might use some other route that goes behind the sea and then goes other way around. So have you heard about data center in a container? I mean, this is not a Docker container. Have you heard about data center inside a container? So they are saying that instead of filling this room with blade servers and storage servers, they just give you a container which is already filled with rack servers, factory topology, storage servers, and you just buy the containers. So what would be the advantage of that? So these are like shipping containers, and they all are filled with computing storage servers. So what would be the advantage of that? Instead of fitting the rack cabinets in this room, I just put a container. The main advantage is that if few blade servers, few racks fails, instead of fixing that, they give you a new container. So it's easy to roll over and fail over. So they provide a data center container as a service. So that's the main service. They provide the whole container. So if a majority of your rack servers inside the container is failed, instead of coming and fixing it, they will just copy all your data and services to the new container and then replace the container. It's much more easy to manage over the lifetime because those containers are sitting in their warehouses where they have configured everything and they just have to come and replace it. They don't have to send a network engineer to this room and fix your servers. It's much more agile for them. It's plug and play. You just have to add electricity and it's pre-assembled. It's cheaper, which is the philosophy of cloud computing. So much easier paradigm for them to manage, to sell the data center. So the main advantages of modular data center is, of course, fast deployment because they don't have to physically come and fix everything on site. They just pre-assemble, pre-configure off-site. They just come, connect the power supply, and your data center is ready to go. Also, it's easy to scale out. So you say that, okay, now I need more servers. They don't have to come and put more rack unit. They'll just give you more container, inter-network using a fatter switch, and then you have a bigger data center. It's ready to scale our data center if you use the modular philosophy. About the cost, it depends because cost is complicated. It depends on what kind of blades you are using, what kind of virtualization you're using. So you can't really say lower cost, but you can say lower cost in the sense that it's easier to maintain and do the failover. But the actual cost can depend on what kind of hardware and networking devices you have inside the container. So lower cost is, we can debate about that.